So I'm going to review a little bit of what we said last time. We have we have a shift map on the one-sided shift space. Mu is Bernoulli measure, it's a product measure, where mu is probability x. And we consider a map function from M to matrices depending only, so locally constants. And this is this means that a of x, 0, x1, xn depends only on x0. That's what I mean by locally constant. So these are the data, and then we consider the linear cocycle given by a over f, so xv goes to f of x, ax of v, and also the corresponding projective cocycle. Okay, and what we are doing is to reveal and explore the connection between Lyapunov exponents of f of these data and invariant measures, and especially stationary measures for these cocycles. So a probability eta on projective space is stationary if for any measurable subset of projective space, the measure of the set is the average of the measures of the pre-images where the average is respect to mu. So in other words, we can represent this in a shorter way by saying that eta is the average of ax star eta. Just take the push forwards of eta with respect to ax, and then you average this out with respect to x. Okay, so that's the well, this is just a way of saying this. This is just notation. But it's perhaps easier to understand what it means to be stationary. And then we have a certain number of properties for these measures. First of all, eta is stationary if and only if mu times eta is PF invariant, which is really the reason why this notion of stationary is useful. So what we have is that this map here has certain invariant measures that are products of mu times something, times some probability here, and these probabilities that appear as factors are the stationary measures. The set of stationary measures is non-empty, compact, and convex. Compact also means that it is closed. So if you have a sequence of stationary measures and you take an accumulation point, the accumulation point is a stationary measure. But in fact, we can say more than that. We can say better than that. We have a stronger property of being closed that is in terms of both the stationary measure and mu. Let me state it properly. Oh, here, yeah. Let me state it carefully. Yes. So it goes like this. The set of pairs nu eta such that eta is stationary. When I said define stationary, it's clear that the measure mu is involved here. And of course A is also involved. So I should say stationary with respect to mu and A. Okay. but I mean that this depends on mu is relevant for what I'm going to say. That it depends on A is not so relevant. So let me look at the set of pairs nu eta such that eta is stationary with respect to mu equals mu to the n. This set is closed. So you have the right to vary the measure here, this probability, and vary the etas as well, and this set is closed. So more precisely what this means is, if you have a sequence of etas converging to nu, of nu etas, nu k, converging to nu, and you have eta k, which is stationary with respect to mu k equals nu k to the n. And eta k converges to eta. You have a sequence of pairs nu k, eta k in this set here, and they converge, then eta is stationary with respect to nu to the n. Okay. Of course, one particular case of this property is if you take this sequence to be constants. And then you are talking of stationary measures for one given system. Now, I have to be a little bit more precise about these convergences. In the generality that I'm writing this here, this convergence, let me explain what I mean by convergence here and by convergence here. Okay, so 2 is easy. 2, I'm talking of weak star convergence. As for 1, I'm not sure we can do this in weak star topology, so I could only prove it for pointwise convergence, which means that nu k of b converges to nu of b for every measurable b. That's one case where the property, the statement is true. I cannot prove it in general just with weak star. But there is one case, one situation where we can get the result with weak star topology, weak star convergence. And that is if we assume that all the functions there are continuous. If we assume that essentially that A is continuous. And both statements are proven in the book. Okay. So if the co-cycle is not so wild, we have the statement both here and here with weak star topology, weak star convergence. Now we had seen that, I also said something about ergodicity. I also said something about ergodicity. We say that eta is ergodic, stationary measure is ergodic. If and only if the product measure is ergodic for projective cocycle. If it is an ergodic invariant measure for the projective cocycle, but then you can characterize in other ways, if and only if eta of b, eta of d is 0 or 1 for any stationary set, eta stationary set. where this property here, to be stationary, means that it means that it satisfies the property. That's not what I want. I have to translate because I defined it for functions. Yeah, so if and only if the characteristic function of D is a fixed point for this operator P. P was the operator defined by this is the definition. So if this means that the characteristic function of D is equal to the integral of, well, I have to write the characteristic function here and then take the measure, so key of V is equal to the measure of the set of points x in M such that ax minus 1 of V belongs to D. I'm just rewriting this relation in terms of with that definition. So in other words, this is 1 if V is in D, and 0 if V is not in D. So the measure of the set, the set of points that, let me just check whether it's the way I defined it is, yeah. Sorry, this is not minus 1. This. So the set of points x such that the image of your vector is in D is 0 if the vector is not in D, is 1 if the vector is in D. It essentially means that if you have a vector that is in D, all the images are in D as well, almost all. And if the vector is not in D, the direction is not in D, then almost all of the images are not in D either. Okay? It's a bit like being invariant. A set is invariant if a point being in the set implies that the image is in the set. A point not being in the set implies that the image is not in the set, except that we don't have an image. We have all the, a whole family of images depending on point x. And so instead of saying that the image is in D, we just say that almost all images are in D, or almost all images are not in D. That's what stationary means. And a measure is, stationary measure is ergodic if these stationary sets have 0 measure or full measure. And then I also stated that that we have an ergodic decomposition theorem that every stationary measure can be written as a linear combination of ergodic stationary measures. So we have two facts, and I will try to prove at least one of them, which is, the first one is that the largest Lyapunov exponent is the maximum of integral of phi d mu times eta, maximum over all stationary measures. And we have Furstenberg's formula, which says that if the co-cycle is completely reducible, then lambda plus is the integral of phi d mu times eta for every stationary measure. Okay. So I will probably skip the first one and tell you about the proof of the second one, which is a big theorem. But before doing that, I want to make an observation that I didn't stress enough last time. Most of the times, it's not so important whether we are working on the one-sided shift or the two-sided shift, because the theories are very much the same. And in fact, in this context, if you have a co-cycle like this defined on the one-sided shift, then you can extend it to the two-sided shift immediately. What do you do? Well, we can go from m equals x to the n to m equals x to the z in the following way. We take the shift. Let me call this m plus to stress the fact that we are one-sided. Only we take the one-sided shift, and we consider instead the full shift, which is perfectly well defined. And we take a function a depending on the zeroth coordinate only, depending only on x0. And it's obvious how to define from it a function on the full shift, depending also on the zeroth coordinates. You just do a of x minus n, x minus 1, x0, x1, xn, you define to be a plus of x0, x1, xn. This is trivial because we are assuming that this depends only on x0. There's an obvious way how to extend to the full shift. And so, given a one-sided co-cycle like this one, we can construct a two-sided co-cycle. And the two co-cycles that I construct in this way, f plus and f, have the same Liapunov of exponents. And the same oscillator flag. When I say the same, I hope you're not too formalist, because these are functions defined in different places, but it's the same in the same sense that A and A plus are the same function. Obvious extension one of the other from the other. The Lyapunov exponents are the same, and the oscillator's flag is the same. And the reason is that if you iterate this two-sided cocycle only forwards, what you are doing is the same thing as iterating this one. The difference between the two is that here, since this is two-sided, you have the right to iterate backwards. And so, in addition to the oscillator's flag, you have an oscillator's decomposition, but not here. Okay? But the exponents, the Lyapunov exponents, lambda 1 through lambda k, can be defined iterating only forward. So they are the same form. So it really doesn't make much difference whether we, in this situation at least, whether we consider one-sided or two-sided shifts. However, some of the statements may depend on that. And this is one of the statements where one uses the fact that it's one-sided. That first statement is not true. Not true. This one is not true for two-sided cocycle case. For the two-sided case. That used to bother me a lot. I was troubled by it. But then I realized that it's one of those things in life that's how it is, and what can you do? It's nothing mysterious. It's just how it is. Okay, and I didn't stress it last time. I don't want to give you the wrong impression. So I'm not going to go into that here, but I want to warn you that in the two-sided, in the invertible case, two-sided is invertible. In the two-sided case, invertible, case, I'm just going to say a few words. I'm not going to do it, but we have two notions. We have a notion of forward stationary measure and backward stationary. So the definitions are more or less obvious. Forward stationary is the same thing as before. Eta d equals ax star eta of d mu x. And backward stationary is similar, except that you iterate backwards. So you use a minus 1 star eta of d. The quick definition is that a measure is forward stationary for f if it is stationary for f plus, and is backward stationary for f if it is forward stationary for f minus 1. Nothing mysterious here. But this is not true for forward nor backward stationary measures. In addition to that, in the invertible case, we have notions that don't make sense in general, and they are called U states. U state and S states. I'm going to explain very rapidly what that is. And these notions are important to develop the theory in the invertible case. A U state is, and then the notion of S state is simple. A U state is a measure, probability measure, on M cross PRD. And now I'm going to draw M cross PRD. This is M. I'd like very much to draw the two-sided shift as a square or rectangle to emphasize the fact that it is a product space. Given a point X, X is a sequence. Okay, I can project this point into its coordinates, positive coordinates, X plus, and negative coordinate, X minus. So what is X plus? X plus is the positive part of the sequence X. And X minus is the negative part. And we have this embarrassing problem of deciding whether 0 is a positive number or a negative number. You put it where you prefer. I like to put it with the positive ones. Okay. So this is a picture of M, and now I'm going to multiply by projective space. Okay, this is PRD. Okay. Now I'm going to explain what it means to be a U state. So M is a U state if the measure of, I can never get this right the first time, so let me look at the M of A minus multiplied by A plus multiplied by B. So A minus is some subset here. Okay, this is A minus. Some subset in the space of one-sided sequences indexed by the negative numbers. A plus is some set here, subset of the space of one-sided sequences indexed by the positive numbers. So A minus times A plus is a little rectangle here. A minus times A plus. And then we multiply by B. B is in the vertical. Well, this would be multiplied by everything, okay, by the whole PRD. I want only a little bit. So I want something like this. Can you see what I mean? You have this product into three factors. You take a rectangle here, multiply by some height. There's some B. B is here. You get some kind of solid. This is A times A minus times cross A plus cross B. So you divide this, the measure, by the measure of the basis. Okay. Think of this as some sort of cube, or a prism over this rectangle. We look at the measure of the prism. We divide by the area of the basis, and we want that this does not depend on A plus. So if you move this picture around, if you move this picture in this direction, if you change A plus, you get always the same quotients. It depends on A minus, it depends on B, but not on A plus. And that's what it means to be a U state. S state would be defined exactly the same, but you say that does not depend on A minus. It does not depend at all on the set. Okay? For those of you who are familiar with the notion of disintegration, I'm trying to avoid using Rochling again. But what this means is that if you disintegrate M into conditional measures, the conditional measures that you obtain are constant along this direction. Okay, and I'm giving a macroscopic. It's proven in the text that equivalently the disintegration, the conditional measures of M along the conditional measures mx depends only on x minus and the S state is characterized by saying that the conditional measures mx depend only on x plus. I'm just giving here a macroscopic formulation of that doesn't need rochling in order to make sense, but that's the same thing. A U state is a measure in this product whose disintegration is constant along unstable, along this positive direction, and that nest state is a measure whose disintegration is constant along the negative direction. Okay. That's proven there. And then the reason, well, one of the various reasons why these measures are relevant is that we have a connection between all these notions that I summarized in this table. And then a large part of the chapter is to prove this table. Eta is forward stationary for F, for the two-sided cocycle, if and only if mu, the measure m plus equals mu plus times eta is pf plus invariant, and that's this is the property that replaces this one. So we already know what F plus is. F plus is just the cocycle defined on M plus. And I didn't say what mu plus is, but well, I did. Mu plus is mu to the n, the Bernoulli measure, on M plus. And so what I wrote here says a measure is forward stationary for F if and only if it is stationary for the one-sided cocycle, and then of course that means that this product measure is PF plus invariant. So this is not new. The other thing I already said, the disintegration mx of m does not depend on the positive parts. It's another way of saying it. And the other condition that connects to the notion of U state and S state is that the lift of M of eta is a U state. M. So I have to explain to what I mean by lift. That is given by the following proposition. Given any PF plus invariant measure M plus on M plus cross PRD, there exists a unique PF invariant measure M on So here I want to, what I mean is, maybe I should write it more differently. I already said that studying the one-sided shift or the one-sided cocycle or the two-sided cocycle doesn't make much difference because they have the same Lyapunov exponents, the same Vasiliadis flags, and so on. But this proposition goes deeper into that. It says that essentially the one-sided cocycle has the same invariant measures as the two-sided cocycle. Because for any invariant measure of the one-sided cocycle lifts to a unique invariant measure of the two-sided cocycle. This pi here, pi is the map from M cross PRD to M plus cross PRD, is the natural projection that takes a sequence and then some direction and maps to, well, what you do is that you forget the negative part of the sequence. And you don't do anything to the direction. Okay, so any measure of invariant measure of the two-sided cocycle may be projected to an invariant measure of the one-sided cocycle. Going this way is easy, and this proposition says that you can also go backwards, that given any invariant measure here, you have a unique lift to the larger space that projects to that M plus. So the two have essentially the same invariant measures. There's a one-to-one correspondence between them. So that's what the lift is saying. Now, I don't expect you to absorb these notions. This is a sort of crash course on the ergodic theory in the two-sided case, but I wanted to point out that the invertible case is, in a sense, richer. You have more objects that you can work with, but it doesn't add much because in the end, I mean, there's essentially a one-to-one correspondence between the two. Okay. All this is done in chapter 5, but I'm not going to go deeper into that here. What I want to do is to tell you how to prove Furstenberg's formula. Let's see. So let me remind you what completely reducible means. Completely irreducible means there exists, does not exist L contained there does not exist a finite family L of subspaces of Rd invariant such that Ax of L belongs to L for every element of this family. So this L here means a subspace, an element of this family, and mu almost every x. But you cannot find a finite family of subspaces that are left invariant by almost all of these matrices. The family that is left invariant by almost all of these matrices. Okay. Okay, this here's a lemma that explains how the assumption is used. If the cocycle is completely irreducible, then stationary measures cannot have atoms, cannot have points with positive measure. But it's more than that. Then eta of V equals 0 for any subspace V of Rd. And any stationary measure. Okay, does this make sense? We are not so used to talking about projective spaces, and I didn't define what is a subspace of projective space, but that's easy. For example, maybe I write it like this. So here V is a subspace of R, D, and I use this to represent the corresponding subspace of projective space, which is just the set of all lines defined by vectors in V. Okay? Projective subspace is the projectivization of a linear subspace. Okay? So these stationary measures can be very general, and I think last time we saw examples where the stationary measures are supported in points, and they are atoms, they are atomic. This lemma says that if the cocycle is completely irreducible, then there are no atoms, and in fact any proper subspace of projective space has measure 0. Okay? That's what the lemma says. So let me prove this. So suppose, this is by contradiction. Suppose there is some subspace with positive measure. First thing I'm going to do is to take the subspace with the smallest dimension. Take V with smallest dimension. For example, it could be that V has dimension 1. Okay. So let's call this dimension D0. Okay. Now I'm going to take delta 0 as the infimum of the measures of the sets formed by where V is a subspace of RD with the smallest dimension. Okay, so first I take the smallest possible dimension, and then among all subspaces of this dimension that have positive measure, I take the smallest of all these measures. Okay? I claim that delta 0 is the largest. Yeah, the largest. The smallest would be 0, the infimum. There could be spaces. So, of course, delta 0 is positive, and delta 0 is attained. By this I mean that there exists some subspace V0 such that the measure of V0 is delta 0, the dimension. So I claim this. So how do I prove this? So, proof of the claim. Take a sequence Vk such that the measure of the Vk's converges to the supremum. Okay. So these are subspaces with dimension d0. Okay. Think of a case where these subspaces are lines. The set of all subspaces with a given dimension, also known as the Grassmannian manifold of this dimension, is a compact subset. So we may suppose, up to taking a subsequence, we may suppose that Vk converges to some V0. For those of you that don't remember that the Grassmannian is compact or don't remember the proof, here is the proof. Take a basis V1, Vd0 for the first subspace. Take a basis for the second subspace. Take a basis for the third subspace. So take basis for all of them. Ordered basis. Look at the first vector in each base. I take orthonormal basis. Take orthonormal basis for each one of these Vk's. Look at the first vector for each basis. That's a sequence of vectors with norm 1. We know that the ball in Rd is compact. So we may find a subsequence of kj's such that the first vectors in the basis converge. Now, restrict to that subsequence and look at the second vectors in the basis. You may find a subsequence that the second vectors converge. And you only have to do this d0 times. You end up with with bases that converge for each. All vectors converge. If you take the basis to be orthogonal, then the limit is a orthogonal set. It generates some subspace, and that subspace is V0. Okay? I can write this down, but this is easier to understand than to write. Okay, so that's why the Grassmannian is compact. But it's a great sentence to tell your friends. Grassmannian manifold is compact. It impresses people when you say it. But it's not so difficult. Okay, so it converges to some V0. Now, if you take a subset of Rd and you look at this bracket V is a closed subset of projective space. If you have a linear subspace of Rd and you take its projectivization, bracket V, that's a closed subset of PRD. Okay? So, since this is closed in PRD, the measure of it is bigger or equal than the lim sup of the measures of the VKs and so it is bigger or equal than delta 0. Okay. It's a property of the weak star topology. The fact that it is closed implies that the measure of this is bigger or equal than the lim sup of the measures of the eta case, which are bigger than delta 0. So, eta of V0 is delta 0, which is what I wanted to prove. Delta 0 is the supremum. I've shown that it is attained. So the supremum is attained. Let us fix V0. Okay. And let us look at the family of images of V0. Okay. All images under all these matrices. Yeah, what I wrote is correct. What I said is wrong. Nothing to do with the weak star topology. You have your set V0. Okay? If you take any open neighborhood, then because these subspaces converge to V0, then for k sufficiently large, Vk is inside. So the measure of any neighborhood of V0 is bigger or equal than the measure of Vk for k sufficiently large. Okay? So the measure of any neighborhood of V0 is bigger or equal than delta 0 for any neighborhood. Now I take the intersection of over all the neighborhoods. If you have a closed set, the intersection of its neighborhoods is the set. So I get this. Okay? So what I wrote is correct, but it has nothing to do with the weak star topology. Okay, so fix V0 and consider the family of all these subspaces. Okay, all the images. I claim that this is a finite family. That's a finite family. It doesn't look like, but it's finite. I want to take the inverse. Let me see. What I said is correct, but I'm not sure that's what I want to do. So these are subspaces. All of these are subspaces with dimension d0. And now I make another claim. My claim is that eta 0, eta of all those subspaces is delta 0 for mu almost every x. This is the best part of the proof. This is the nicest part of the proof. Let me argue like this. eta of v0 is the integral of eta of this because eta is stationary. Okay? Now, this is equal to delta 0. And this is less or equal than delta 0 because delta 0 is the supremum. Okay? So here we are integrating a function with respect to a probability. The function is always smaller than delta 0, and yet the integral is equal to delta 0. Okay? So it has to be equal to delta 0. Mu almost everywhere. End of the proof. So now let me call L the set of all subspaces of dimension d0, all subspaces v0 of dimension d0 with such that the measure is delta 0. Okay. So what do we know up to this point? We know that L is non-empty. And we know that if v0 is in L, then ax minus 1 v0 is in L for mu almost every x. And now I make a final claim that L is finite. And this will be the L that we were looking for. Already raised the statement, but this is our L. The set of subspaces with the smallest dimension and the largest measure is non-empty, invariant, and finite. So suppose that you have V1, Vn in L, all distinct. The smallest dimension. I'm not saying disjoint, I'm saying distinct. Disjoint would be cheating. I want to prove that there are at most this number of subspaces. So I take certain any family that is contained in L, all distinct. And now I claim that I look at the measure of the union. Well, this is, of course, is less or equal than 1. And I would love to say that this is the sum of the measures of each one of them. If they were disjoint, I would be able to do that. And then this is equal to n times delta 0. And that would imply that I have at most 1 over delta 0 distinct elements in L. So to make this argument work, I have to explain why this is true. And the reason is that if I take any of them, if I take 2 of these, they are subspaces with the dimension d0. The intersection of 2 subspaces of dimension d0 is a subspace with dimension strictly less than d0. Right? And so the measure of the intersection is 0 for all I and all j. Because I chose the smallest dimension for which there exists some subspace with positive measure. So they are not disjoint, but for all practical purposes, they are disjoint. Okay? It's a beautiful argument. As far as I know, it was invented by Furstenberg. It's a beautiful argument. Combines several ideas, but the nicest ones, in my opinion, are the fact that we took the supremum so that this formula implies that all the measures have to be, or almost all of the measures have to be delta 0. Once you know that the integral is maximum, the function has to be maximum almost everywhere. And the other one is this quasi-disjointness argument, and that's the reason why we took the dimension to be smallest. Really beautiful argument. Okay, so what did I get? I found a family. Oh, I have to conclude, right? So L contradicts the assumption that the cocycle is completely irreducible. Okay? So if I have subspace with positive measure, then I can find this family, the family of all subspaces with smallest dimension and largest measure, and it contradicts, it has this property, and contradicting the assumption that the cocycle is completely irreducible. Mm-hmm. I'm thinking of the shortest way to answer. It's the same. That's the shortest answer. Because this is a finite set. And if you have a finite set and all the pre-images are contained in this set, then the ax minus 1 is a bijection from L to L. And that also means that the image is in L. Okay? Once you know it's a finite set, it doesn't really matter. But the easiest way to make it clean is to put a minus 1 here. Now it's official. It's really the same. I think in the text, notation is a little bit more consistent. Okay, so how do we proceed with the proof of Furstenberg's formula? So we are proving this, right? So we take M. This we know is PF invariance. So we may use the ergodic theorem. We've done this before. The ergodic theorem tells us that this limit 1 over n sum phi pf j x v is exists almost everywhere. Exists for m almost every x v, and we also know that this is equal to the limit 1 over n log of a n x v. You just have to replace phi by its expression. And also, this I call C, just notation, or phi twiddle. And it satisfies that the integral is the integral of phi with respect to m. This is just the an argument based on the ergodic theorem that we used a couple of times at least before. Now, we also know that. So we want to prove that this is equal to lambda plus, right? We want to prove that the integral of phi dm is equal to lambda plus, which is lambda 1. Okay? Now, we know that since we have this relation here, we know that phi twiddle xv is equal to lambda 1 at the point x. It doesn't matter because I'm in the ergodic situation. This does not depend on x. For every v in v1 minus v2. Okay? This v1 and v2 are the first two subspaces in the oscillated's flag. So we want to prove this. We know that the integral of phi is equal to the integral of phi twiddle, and we know that phi twiddle is equal to lambda 1, to the thing we want, whenever the vector is outside the second subspace in the flag. Okay? Now, this is again the same kind of situation. This function is at most lambda 1. I want to prove that the integral is lambda 1. So I have to show that the places where it is small, or where the function is smaller than lambda 1 has zero measure. So we need to prove it's so we need to prove that the set of pairs where the equality is not true has zero measure. Okay? So you have this projective space. Your stationary measure is there. We are looking at the product. And in projective space, we have a bad subspace Vx2. I'm representing this as the sort of equator of the projective space. This is PRD. This is where the exponent, the function phi twiddle, is smaller than lambda 1. And we have to prove that that locus is of zero measure. It's necessary and sufficient to prove that. Okay, but since our measure m is mu times eta, the measure of this set is the measure of Vx2, and then you integrate with respect to mu. Right? You have a measure, you have a set, it's a graph of Vx2. So each point x, you associate corresponding Vx2. Then the measure, the product measure of this graph is just the integral with respect to mu of the measures you get on the slices, on the vertical slices. Right? Now the lemma says that any stationary measure gives zero weight to any subspace. Okay, end of the proof. Stationary measures of completely irreducible cocycles refuse to be constrained inside subspaces in any sense. Some people call this property being quasi-absolutely continuous, which is exaggerated. But it says in the sense that the measure is spread out in the whole projective space. It's not contained in anything that is of strictly smaller dimension. Okay, I think that's all I'm going to say about this here. My plan is, we are getting very close to the end of the summer, so my plan is to start to converge. In the next few lectures I will be talking about continuity, which uses these ideas. And I won't be able to lecture tomorrow because we have something going on, but we continue on Thursday. Okay? And we'll focus on continuity. questions? Ok. Amanhã não temos aula, continuaremos na quinta.